All right, I think we're testing ControlNet. ControlNet. Let's see if the audio works. I don't know if the audio is working. Not? Test? Okay, it seems like it does work. Oh, Dr. Prince. All right. Get started today. The exciting day today. We're going to be looking at ControlNet. So ControlNet has been taking the internet by storm. This is a diffusion model, specifically kind of modifications onto the Stable Diffusion model. And this repo is out of control. This repo has over close to 7,000 stars, and it was released basically a couple weeks ago. So the speed at which the internet has decided to adopt ControlNet is absolutely insane. Contributions are still super active. Look at this. Yesterday. So this repo is getting contributed to immediately. We're gonna get into this. We're gonna read the paper for it. But basically, what ControlNet allows you to do is it allows you to control diffusion models. So diffusion models have been useful in kind of text-to-diffusion mode, which you kind of write a bunch of text and then the diffusion model creates an image, right? But it's been very difficult to control them, and it's very difficult to create the exact image that you want. So now with ControlNet, you can basically specify maybe the edges of something and have much more fine-grained control over what the actual final output looks like. So you can see here, given this kind of like the edges of this room, right? The edges of the kind of like, you could think of it almost like a coloring book picture, right? Stable Diffusion will fill in the blanks. And this is incredibly powerful. People are feeding in entire movies frame by frame. They're basically, it seems like this has opened the floodgates for all different types of content creation, right? Like, just look at this, right? You can take a picture of a backpack. Now you can turn it into any backpack. But, you know, this type of stuff was possible before, but now really the huge step function improvement here is the level of control, right? Where you can basically control exactly what you want the backpack to look like, right? And it's not just limited to edge images like that. You can also feed it things such as a pose. Look at that. This is crazy. So, long story short, I'm pretty excited. There's a lot of activity, a lot of hype. People are going pretty crazy with this. It seems like it's incredibly useful. And because this is the Hoopo channel, we're going to dive deep. We're going to go right to the paper. So ControlNet is based on this paper here, adding conditional control to text-to-image diffusion models. This is a paper written by, not what I want, this in paper pile. So this paper is written by the people here. We have LV Min Jang and Manish Agrawala from Stanford. So if we actually look at the contributors for this GitHub repo, this is actually the LV Jang, and then I assume this is probably, no, this is different guy, that's a different guy. So actually, ControlNet seems to basically be the work of this guy here, right? You look at the contributions, it's almost entirely this person. So seems like it's mostly this person, and then I guess this is probably the advisor. So really recent work, 10 February 2023, and of course the GitHub repo itself is really only February 5, so this stuff is fresh off the press. Let's get into it. We present a neural network structure, ControlNet. Okay, this is interesting. I'm calling it a structure, right? It's not. They're not calling it a pipeline. They're not calling it or model architecture. They're calling it a structure. You control pre-trained large diffusion models to support additional input conditions. So this is basically a good little summary. The ControlNet learns task-specific conditions in an end-to-end way, and the learning is robust even when the training dataset is small. Moreover, training a ControlNet is as fast as fine-tuning a diffusion model, and the model can be trained on personal devices. Does that mean cell phones? Probably not. It probably means like GPUs at home. Alternatively, if powerful computational clusters are available, the model can scale to large amounts, millions of data. We report that large diffusion models like Stable Diffusion can be augmented with ControlNets to enable conditional inputs like edge maps, segmentation maps, key points, and etc. Right? So it's still to be determined how much more stuff you can use to control a diffusion model, which is exciting to think about. This may enrich the methods to control large diffusion models and further facilitate related applications. Yeah, I think that already if you go on the subreddits and you go on Twitter and these different communities, you're going to see all kinds of interesting stuff that people are finally able to do with diffusion models. All right. So with the presence of large text-to-image models, generating a visually appealing image may require only a short descriptive prompt. After typing some text and getting the images, we may naturally come up with several questions. Does this prompt-based control satisfy our needs? Yeah. I think this is an important thing to ask, right? Where it's prompt-based control was very crazy in terms of kind of the step function, right? We really opened our eyes to the capabilities of models and the fact that they can understand and interpolate between language space and image space. But realistically, it's not, we need more control, right? If we want to start making actual content, actual images that are useful in some kind of application, we're going to need to go beyond just prompt-based control. We need more fine-tuned control of these image generation models. So I like how this paper starts off with kind of the idea of, hey, let's actually think if prompt-based control is enough to satisfy our needs, right? They start by putting into question the idea that our future would be dominated by prompt-based control of AIs and not more fine-tuned control of AIs with things such as edge maps, segmentation maps, and so on. For example, in image processing, considering many long-standing tasks with clear problem formulations, can these large models be applied to facilitate these specific tasks? What kind of framework should we build to handle a wide range of problem conditions and controls? Yeah, wide range of user controls. In specific tasks, can large models preserve the advantage and capabilities obtained from billions of images? We investigate various image processing applications. Available data scale in a task-specific domain is not always as large as that in the general image text domain. Largest dataset size for many specific problems is often under 100K. Okay, this would require robust neural network training to avoid overfitting and to preserve generalization. So I think the way that most people have kind of been doing this for the past, 10 years is basically you have a pre-trained model that used to be trained on, for example, ImageNet, and then you would fine-tune it on your smaller task-specific problem. So the current paradigm for computer vision has been pre-training on something like ImageNet and then fine-tuning on your specific application. So Second, when image processing tasks are handled with data-driven solutions, large computation clusters are not always available. This makes fast training methods important for optimizing large models to specific tasks within an acceptable amount of time and memory space. This would further require the utilization of pre-trained weights as well as fine-tuning strategies or transfer learning. Okay, so this is basically what we're saying, right? That you start with some pre-trained model that's pre-trained on the biggest possible data set that's as broad as possible, and then you fine-tune it or transfer learn. Fine-tuning and transfer learning are basically the same thing at a high level. It's this idea of taking a model which is trained on one specific data set, one specific distribution, and shifting it such that it can perform well on a different distribution, right? So that's what the transfer in transfer learning means, where you're transferring the distribution that the model is good at, or the model is supposed to interpolate well within the distribution that it's trained on. So by fine-tuning it on a new data distribution, you are hopefully transferring its ability to interpolate in the larger training distribution that it was originally pre-trained on, and you're transferring that to the smaller distribution of your task-specific problem. Third, various image processing problems have diverse forms of problem definitions, user control, or image annotations. Although an image diffusion algorithm can be regulated in a procedural way, behaviors of these handcrafted rules are fundamentally prescribed by human directives. Considering some tasks like depth to image, pose to human, these problems essentially require the interpretation of raw inputs into object level or scene level understanding, making handcrafted procedural methods less feasible. To achieve learned solutions in many tasks, end-to-end learning is indispensable. Okay, so here we have a very nice, well illustrated, very clear example of ControlNet. So this is the original image here, right? This seems like a real image, like an image of a deer, I guess, or an elk. I don't know what this is. But here you have the Canny edge. So Canny edge detection is an algorithm for determining the edges of images, or the edges within an image. So this is an old school computer vision algorithm. This is not recent. This has been out for a very long time. Can we actually see on Wikipedia when it was originally created? Created. Okay. Maybe we don't have the date, but basically the way that okay, here we go. It was developed by John F. Canny in 1986. So this is quite old now. And basically the way it looks is it looks for the gradients. So basically anytime you have within an image, you have basically in the pixel values, you're going to have a certain color, and then suddenly it's going to change to a different color, right? So here on this picture of this elk, the body of the elk has a certain color, has a certain kind of distribution to the pixel values, and then there's going to be a different distribution of pixel values for the background, this fog, right? So if you were simply plotting the value of these pixels, right, it would kind of be this like brown, 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 and then suddenly poof, it would drop really quickly and become this like kind of more grayish color. So that instantaneous change from this kind of brown into this kind of white, you could actually detect that quite easily, right? It's like you don't need any kind of advanced algorithm to really detect that edge. It's actually quite obvious, and you're just basically taking a gradient, right? Or not a gradient, but the right word. Gradient magnitude. There you go. So you're saying how much do these values change from the pixels to the left of it and the pixels to the right of it, the pixels on top of it, the pixels to the bottom of it, and so on. Compare the edge strength of the current pixel with the edge strength of the pixel in the positive and negative gradient direction. So positive and negative gradient directions here just means you're moving this way or this way, right? But long story short, I'm kind of getting stuck here on canny edge detection. But long story short, it's a way to feed in this image and get this image, which is a black and white image of basically all the areas of the image where there's a large change in the gradient, right? And that's kind of, it's not necessarily perfect. Like you can see here, there's parts of the image that don't have an edge, right? There's probably too many edges here and so on. But what ControlNet allows you to do is it allows you to take a diffusion model and constrain it such that this edge input is somehow used. Not 100% sure exactly. That's what we're going to figure out today. Canny edge map is an input, and the source image is not used when we generate images on the right. The outputs are achieved with a default prompt, high quality, detailed, and professional image. This prompt is used in this paper as a default prompt and does not mention anything about the image contents. Most figures in this paper are high resolution images and best viewed when in. So the only thing that the diffusion model is getting is it's getting this prompt, and then it's getting this canny edge as the input. So it does not know this original image. And you can see here how, like, given the extra constraint of this canny edge, it's just so much cleaner. Right? Like, all the horns in every single one of these images is basically perfect. Or at least perfect when reference to the source image, right? Look at the lighting that goes through these horns. Look at the lighter tips of these horns. So this is quite impressive. This paper presents ControlNet, end-to-end neural network architecture that controls large image diffusion models to learn task-specific input conditions. The ControlNet clones the weights of a large diffusion model into a trainable copy and a locked copy. Okay, so we're starting to learn exactly how this works. The locked copy preserves the network capability learned from billions, while the trainable copy is trained on task-specific data sets to learn the conditional control. We're going to have two different copies of the model. Okay, so how are these going to interact together? The trainable and locked neural network blocks are connected with a unique type of convolutional layer called a zero convolution. There we go. Where the convolution weights progressively grow from zeros to optimize parameters in a learned manner. Okay, so there's kind of some interesting initialization going on here. Since the production-ready weights are preserved, the training is robust at datasets of different scale. Since the zero convolution does not add new noise to deep features, the training is as fast as fine-tuning a diffusion model compared to training new layers from scratch. Okay, interesting. So what they're mentioning here is that when you train new layers from scratch, the way that the weights inside those new layers have been initialized, usually it's some kind of random or something that is supposed to be as random as possible, right? There's different forms of initialization, such as Xavier initialization. But here, because they have these convolutional layers, that they're calling zero convolution, right? They start from zeros, right? So they grow from zero, which means that you don't need to push as many gradients, right? Because you're not trying to overwrite the noise that has been that you would normally have if you initialized a layer with something like Xavier initialization. Here, all the layers on the zero convolution they're all just zero. The weights for those are just zero. So very quickly you start pushing a little bit of gradients in there, and it will very quickly get to a point where it's usable. So that's the advantage that they're calling here, is that the training is as fast as fine-tuning a diffusion model. Normally, starting from zero like that would make the model basically very difficult to train. It would be like the reason people don't initialize the weights of a neural net with zero is it's basically not going to do anything. and you're not even going to get it to train initially. That's why you initialize it with random weights. But here, because these layers are, I guess, are tied and connected, we don't know exactly what connected means yet, but they're connected in such a way with the pre-trained Stable Diffusion that you do get kind of some stability, and the model is able to learn. We train several control nets with various data sets of different conditions. Okay, so Canny edges, puff lines, user scribbles, human key points, segmentation maps, shape normals, depth. So these are all different types of labels. I don't know if labels is the right word, but basically key points, segmentation maps, these have normally been the output. So for most of computer vision, you've been given an image, and then then you want an edge map, right? Or a segmentation, or normals, or a depth image, or key point. So normally these were the outputs of a computer vision problem, and the input would be something like this. So it seems like they're kind of bringing back this all the different computer vision algorithms of ancient times, and using the output of those ancient computer vision algorithms as the input to control a diffusion model. So this is quite impressive. We also experiment control nets with both small data sets, samples less than 50K or even 1K. Okay, so this is what they're calling small data sets is 50K, and large data sets, millions. We also show that in some tasks like depth to image, training control nets on a personal computer, so one NVIDIA RTX Ti, we might actually have a GPU that's better than that in this computer, can achieve competitive results to commercial models trained on large computational clusters with terabytes of GPU memory and thousands of view history on Wikipedia to check the date. You're talking about the Canny edge detector that we did end up finding. It was the second sentence. I scrolled too deep, but they actually tell you right there. So 1986 is when the Canny edge detector came out. And for example, we can do another one here, Huff lines. Huff transform. So this is even older, 1972 and 1962. So yeah, these are very ancient computer algorithms. Related work, hypernetwork and neural network structure. Okay, so here they're going to probably just introduce diffusion models. Hypernetwork originates from a neural language processing method to train a small recurrent network to influence the weights of a larger one. Okay, so this might actually be where they get this connection, right? So they introduced here this concept of having a trainable and then a locked neural network. So two different neural networks that are basically connected layer by layer. So, and then one of them starts at 0. So this is kind of a weird little setup here. So it seems like this is actually where they're getting that weird setup. So the original paper where they have this kind of weird setup here is called hypernetwork. And it's originally a natural language processing, neural language processing. That's unusual, usually called natural language processing, to train a small recurrent neural network to influence the weights. Successful results of hypernetwork are also reported in image generation using a generative adversarial network. Okay, so it seems like people did use this in GANs back in the day as well, and other machine learning tasks. Provided a method to attach a small neural network to Stable Diffusion so as to change the artistic style of its output images. Okay, so actually people have also applied this to Stable Diffusion. So this idea has actually been around originally from NLP, but it's been used in GANs, and it's also been used in diffusion models. This approach gained more popularity after 28 provided the pre-trained weights of several hypernetworks. ControlNet and hypernetworks have similarities in the way they influence the behaviors of neural networks. Okay, so it does seem like there has been some previous work in this type of technique. ControlNet uses a special type of convolutional layer called a zero convolution. Here we go again. We're going to figure out exactly what that means. I think there's some architecture diagrams down here. So yeah, neural network block. And then this is the zero convolution. Trainable copy, zero convolution. ControlNet. We show the approach to a ControlNet to an arbitrary neural network block. X and Y are deep features in the neural network. So this is just the input and output. So generally, the input to a neural network, the symbol X is used, and then the output or the target is Y. But this neural network block doesn't necessarily have to be the entire neural network. It could just be a little piece of that. So what it's receiving is just the output of a previous layer, and what it's outputting will just be the input to the next layer. The plus refers to feature addition. The C is an extra condition that we want to add to the network. The zero convolution is a 1-by-1 convolutional layer. Okay, here we go. With both weight and bias initialized as 0. Okay, so this is going to be where we're going to input our condition, right? Which is going to be the edge detection, or the edge image, or maybe the depth image. And then it's basically going to combine the input X with the condition. I don't know what this is. Maybe it's a sum. Then a trainable copy. This is going to be the actual layer where you're going to push the gradients, right? So over time, I think you're going to fine tune this. That's what I suspect, is you're going to fine tune this ControlNet. And zero convolutions, because they're a 1-by-1 convolution, it doesn't change the size of the input, right? If you have a 3-by-3 kernel when you're doing a convolution, you're going to change the size of the input. But a 1-by-1 convolution is not going to change the size of the input, right? So that's important to remember here, is that this zero convolution being 1-by-1 is not going to change anything. Okay, let's go back here. Early neural network studies have extensively discussed the initialization of network weights, including the rationality of initializing the weights with Gaussian distributions and the risks that may incur by initializing the weights with 0. Yeah, so this is kind of what we were referring to, where kind of common sense is that you don't want to initialize neural networks with a bunch of 0 weights. You want to have kind of a nice little Gaussian distributed noise where everything is nicely shaped. And there's all kinds of techniques that people have settled on. And it's actually at the point where most people, when you're doing any kind of deep learning, you're not really thinking about the weight initialization. You just kind of, whatever the generic weight initialization that PyTorch and TensorFlow have implemented, you're just using that. Blah, blah, blah. Discussed a method to scale the initial weight of several convolutional layers to improve the training, which shares similarity with the idea of zero convolution. Manipulating the initial convolutional weights is also discussed in ProGAN and StyleGAN, as well as noise-to-noise. Stability's model cards also mention the use of 0 weights for layers. Oh, interesting. Okay, so maybe there's less agreement here than I think. Maybe that the initialization has been kind of a point of contention in a bunch of these different models, right? It seems like during the GAN era, people were messing with it. It seems like people have been messing with it for these diffusion models as well. So I don't know, maybe there's something to rethinking about how we initialize neural networks. Diffusion probabilistic model. Diffusion probabilistic model was proposed in 52. Successful results of image generation are first reported at large scale, or small scale, then large scale. Here you go, your denoising diffusion probabilistic model, and then your denoising implicit model. Score-based diffusion, so this is just a kind of like a little summary of diffusion models. Image diffusion methods can directly use pixel colors as training data, and in that case, researchers often consider strategies to save computation power when handling high-resolution images, or directly pyramid-based or multiple-stage methods. Methods essentially use the UNet as their network architecture in order to reduce the computational power based on the idea of a latent image, approach of a latent diffusion model. So this is something that we saw even just earlier this week, where basically you perform the diffusion on a latent version of the image as opposed to the actual image. So the actual image is going to be much higher dimensional than a kind of compressed latent version of that image, right? Which you could think of it like a feature, right? At the end of the day, a feature is anything that is outputted by a layer, neural network layer, and your neural network is basically projecting information from one space that has some dimensionality, right? Like the original input image has some dimensionality, and then it can project it into different dimensionalities. So the latent image is basically just your image projected through a neural network into a lower dimensional space. And in this lower dimensional space, the image also is like a point in that lower dimensional space, and that's what that latent image is. But because that lower dimensional space has less total amount, less pixels, right? Less pixels, less numbers, it's easier to manipulate that than it is to manipulate the original image, which has many more pixels, many more numbers. Text-to-image. Diffusion models can be applied to text-to-image generation tasks to achieve state-of-the-art image results. This is often achieved by encoding text input into latent vectors using pre-trained language models like CLIP. Yeah, so a lot of the success of kind of text-to-image and stuff like that is because you had at one point models like CLIP, right? So CLIP is a contrastively trained contrastive language image pre-training, where basically they're feeding in language and images at the same time, and then the output space of the CLIP model is basically has knowledge of both language and images. So you can take text, turn it into an embedding vector or a latent vector, and then turn images and turn it into a latent vector, and then you can actually compare the distance between those. CLIP is responsible for a ton of kind of the success of text to image. Glide is a text-guided diffusion model supporting both image generating and editing. Disco diffusion is a clip-guided implementation to process text prompts. Stable diffusion is a large-scale implementation of latent diffusion. And image gen. Image gen is the one, I'm pretty sure. Okay, so text-to-image diffusion is really where I think most of the hype has been. What's your opinion about AWS Hugging Face partnership? AWS probably feels left out of the AI race, and HF has a bloated valuation and is looking for an exit. So both parties win if Amazon acquires. What I think. I think Amazon is going to acquire a AI company. Hugging Face is a good target. Stable Diffusion or Stability AI is a good target. Midjourney is a good target. There's a lot of good ML companies, AI companies that Amazon could acquire. I don't think Stability AI will get acquired just because the Emad, the founder, or I guess CEO, I don't know exactly what Emad's title is, but he seems pretty dead set on open source and kind of that whole thing. So maybe he doesn't sell it, but maybe he does. Personalization, customization, and control of pre-trained models. Because state-of-the-art image diffusion models are dominated by text-to-image methods, the most straightforward ways to enhance the control over a diffusion model are often text-guided. Type of control can also be achieved by manipulating clips. The image diffusion process by itself can provide some functionalities to achieve color level detail variations. Image diffusion algorithms naturally support inpainting. Textual inversion and Dream Booth are able to customize. So yeah, we've seen a couple different ways of kind of using diffusion models to do different things. So I think inpainting is one that everybody's kind of seen now, where you can basically mask out certain parts of an image and fill them in with a diffusion model. Image to image translation. we would like to point out that although the ControlNet and image-to-image translation may have several overlapped applications, their motivations are essentially different. Image-to-image translation is targeted to learn a mapping between images and domains, while a ControlNet is targeted to control a diffusion model with task-specific. Okay. Pix2Pix presented the concept of an image-to-image translation, and early methods are dominated by conditional generative networks. So again, any neural network, you can change the inputs and the outputs, right? You can basically feed it arbitrary things, and when you are feeding a neural, or when the input to a neural network, you can say that you're either feeding it to the neural network. That's one kind of way to say it. But another way to say it is that you're conditioning the neural network on an input, right? So the idea of conditional neural networks is that you're conditioning the neural networks on something. And in here, I guess what they're referring to here is that in Pix2Pix, they're conditioning it on an image, maybe? Normally, the conditioning is a text. So the latent vector coming out of a text model, what people are conditioning models with. After Transformers and Vision, Transformers gained popularity. Give me 1 second. Oh, I hit refresh. Go back down. We discussed the strongest methods in image-to-image translation, transformers, vision transformer with a capability to both generate images and perform image. Palette is a unified diffusion-based image translation framework. PITI is a diffusion-based image translation method that utilizes large-scale pre-training as a way to improve the quality of generated results. Specific fields like sketch-guided diffusion. Optimization method that manipulates the diffusion process. Okay. So this has basically just been the related work section. So they've just kind of talked about a bunch of different other papers and everything from kind of where they're getting their zero convolution kind of idea, diffusion models in general, text-to-image diffusion, kind of the models there, and then the different versions of kind of control and customization that you've had for diffusion models. But up until now, this has all just kind of been a summary of different works that they've been inspired by. And now section 3, the method, this is where they're actually going to explain exactly what their ControlNet does. So we're finally at the point where we're going to learn what ControlNet is. ControlNet is a neural network architecture that can enhance pre-trained image diffusion models with task-specific decisions. First sentence, very well chosen, describes everything in one sentence. We introduce ControlNet's essential structure and motivate of what? This is a typo here. We introduce ControlNet's essential structure and motivate of each part. Improper English. We detail the method to apply ControlNet's to image diffusion models using the examples of Stable Diffusion. 2. We elaborate the learning objective and general training method, describe several approaches, and improve the training in extreme. So interesting. They're going to show you what the difference is when you're training on a laptop versus a large-scale computing cluster. I wonder how much of the Stable Diffusion community is actually using laptops and how much of the Stable Diffusion community is actually using clusters. ControlNet. ControlNet manipulates the input condition of neural network blocks so as to further control the overall behavior of the entire neural network. Herein, a network block refers to a set of neural layers that are put together as a frequently used unit to build neural networks. Okay, so basically any subset of a neural network architecture is a block. So a ResNet block, conv block, multi-head attention block, a transformer block. So basically take any neural network architecture, cut it up into pieces, and then any one of those pieces, you can call it a block. I think that's pretty standard terminology there. Using 2D features as an example, given a feature map, okay, so we finally have some math definitions here. We have a feature map X, and the dimensionality of this feature map is H by W by C, where H, W, and C are height, width, and channel, right? So an image is going to have 3 channels, right? A channel for the red pixels, channel for the blue pixels, channel for the green pixels. And images are going to have some height and some width, right? Generally, when people use the word feature map, you're not talking about an image. Now you're talking about kind of an intermediate representation within your neural network, right? So this is not the very, very first input, which is the image. This is going to be basically one of the layers in the middle, right? As soon as you kind of feed something through a neural network layer, it kind of becomes a feature. So rather than say like for example here, the latent image here, another way to say that is basically a feature map. These are basically tensors that have the same kind of dimensionality, right? They have some depth, they have some width, and they have some height, and then roughly spatially, there's some notion of like space in there, right? The height and width are in a convolutional layer. Sometimes the feature map is the result of the convolution with the kernel. So the notion of like this corner of the image corresponds to this corner of the feature map, this corner of the image corresponds to this corner of the feature map is preserved. So the spatial structure of the image and the scene is preserved within the feature map. A neural network block F with a set of parameters theta. So this is just a generic, anything could be, this could be anything. This could be a transformer block. This could be a conv block. This could be just a fully connected multi-layer perceptron. So you just have some neural net F, which is parameterized by some weights and biases and parameters theta. So you have a pretty standard equation that just represents a generic neural net that takes some input X, has some internal weights and biases and parameters theta, and then does some kind of multiplication or some combination of those things, and then outputs y. We lock all the parameters in theta and then clone it into a trainable copy, theta copy. Okay. So this is basically going to be the exact block, but a copy of that block. The copy theta c is trained with an external condition vector c. Okay, so now you have a condition vector c. So they say vector here, right? So in these examples, this is a Canny edge image. This is just a 2D image, right? Or yeah, this has a height, a width, and channels, but here they say condition vector c. So at some point, they're going to have to convert this image or this Canny edge into some kind of vector. So we'll see what they do here. In this paper, We call the original and new parameters the locked copy and trainable copy. Motivation of making such copies rather than directly training the original weights is to avoid overfitting when dataset is small and to preserve the production-ready quality of the large models learned. The neural network blocks are connected by a unique type of convolutional layer called zero convolution, by one convolution, with both weights and biases initialized with zeros. We denote the zero convolution operation as Z. This is going to be their special zero layer. Use two instances of parameters to compose the control net. Okay, so this zero convolution has some parameters theta as well, except here they're going to be calling it theta z1 and theta z2. So you can see here how the zero convolution Z, it takes as input C, the condition vector, and one of these, right? So basically it seems like there's going to be two different versions of this zero convolution. So first thing you're going to do is your network F is going to take as normally you would just have the input X, right, as in here, but you're going to add to that input the zero conv, what comes out of the zero convolution, right? And then the output of that here, right, so this would be Y, right? So Y, you can think of all of this as Y, is going to be fed into the zero convolution again, except this time the zero convolution is parameterized by theta C. So copied weights, right? Or no, here, the F here is with the weights. So the copied weights are for F. So anytime you see theta or theta C, those are the weights of F. Anytime you see theta Z1 and theta Z2, those are the weights of the zero conv. So the zero conv is being applied to the context vector or condition vector C, and then it's being applied to the output of the copied weights of the block F. And then you're adding that to F with the original weights. Then here they say YC becomes the output of this neural network block. So this is basically the image that we saw here, right? So now we know that here it's just addition, right? They're just adding. So basically you take your context, I want to keep saying context, but it's conditioned. So you take your condition vector C here, you feed it through your zero convolution, right? Which has Z1 or theta Z1 here, right? Then you add to it your X, right? You're adding your X here. Then you have the trainable copy, which is this one here, theta C. So this is F, and then this is F parameter. This is F parameterized by theta, and this is F parameterized by C. So you have theta and you have theta C. So here is F parameterized by theta, which is locked, and then you have F parameterized by C, which is the copy. You feed it through the zero convolution again. So this is the outer Z here, and this one here is parameterized by theta Z2. So you have theta Z1, theta Z2, theta C, and then theta. And then you simply just add it to the output. So Y here is just the output of F of X plus theta, which is locked. So that's roughly what's happening here. Because both the weights and the biases of a zero convolution layer are initialized as zero, in the first training step we have, okay, so what they're saying here is that all the weights here, right, all these weights, theta Z1, they're all just zeros. So if you multiply anything by zero, you're just going to get zero. So you're basically going to have zero here. That means that because this is zero, they can simplify this equation, right? So if you plug in zero into here, you basically get f of x plus 0, which means you can get rid of the 0. Now you just have f of x theta copy. So this is this blue one here, remember, right here. And only at the very first step, so that's important, only at the very first step are these both the same, right? Because the copied weights and the weights are the same. But as soon as you push one gradient step, this is no longer true. But because these are the same, you can then substitute them in here, which I think is what they're going to do. So z f of x c theta 1, theta 2. Yeah, so they're basically getting rid of this part here, right? They're just turning it into x. And because all the weights are 0, you can just say it's 0. So I don't know exactly what the point of this equation is. They're basically just saying everything is 0 at the first step. And this can be converted to yc equals y. Yeah, if everything is 0, then you're basically taking c, you're multiplying it by 0, you're adding x to 0, feeding it through here, multiplying it by 0, and then adding 0 to y. So you're just going to get y equals yc. The first training step, all inputs and outputs of both the trainable and locked copy are consistent with what they would be if the control net does not exist. Yeah, because it's all just zeros. In other words, when a control net is applied to some neural network blocks before any optimization, it will not cause any influence to the deep network features. The capability, functionality, and result quality of any neural network block is perfectly preserved, and any further optimization will be as fast as fine-tuning. I don't really know what they're trying to say here. Basically saying if you leave all of these weights as zeros, then it's as if the control net wasn't there. But what's the point of doing that, right? We briefly deduce the gradient calculation of a zero convolutional layer, considering a 1x1 convolutional layer with some weights and biases. So, okay, they're going to maybe do a little bit. Weights and biases are in here. So the weights and biases would be part of the theta z1 and theta z2. At any spatial position p and channel-wise index I, given an input map I, forward pass can be written as okay. So input map I here. So here the C, right? So the input to the zero convolution was originally, they called it a condition vector C, but now here it's an input map. So H by W by C. So C, damn, this is no good, right? There, C is being used as both the variable for the channels, and it's also being used as the variable for the condition vector. So a little unfortunate here that they're using the letter C for two different things here. But here, the C doesn't refer to the channel, or doesn't refer to the context vector. It refers to the number of channels in the input. So you're feeding in some kind of intermediate feature map, right? And your zero convolution has some parameters W and B, and in order to get the output, right, this is basically just what deep learning is right here. You're just multiplying your input by your weights and then adding the biases. This is just like a standard neural network layer, right? Since zero convolution has W equals 0 and B equals 0, for anywhere with I, Pi being non-zero, okay, so any point in the input feature map that is not 0, the gradients become, so this D here means basically derivative. So the derivative of this model with respect to the biases, right? The derivative of this conv0 block or model or layer or whatever you want to call it with respect to the input, and then the derivative of Z, that layer, with respect to the weights, right? And this is how you, so how do you adjust the bias and the weights of a neural network with gradient descent? You calculate the partial derivatives, and then that gives you basically the direction that you want to move in, right? The gradient in that specific parameter, right? So this will be the gradient on the bias, this will be the gradient on the weights, and so on, and then you can basically add that to the current value. But because these are all 0, it's just everything's basically going to be zeros. So, except for here, because the partial derivative is 1, because this is just being this is a summation. So the way that the derivatives work, it's just 1. But this is still just seems like nothing to me. I don't know what they're kind of going for here. They're basically just like, they keep showing equations where they say if we multiply everything by 0, you get 0. And we can see that although a zero convolution can cause the gradient on the feature term I to become 0, the weights and biases gradients are not influenced. As long as the feature I is non-zero, the weight W will be optimized into non-zero matrix in the first gradient descent. Notably, in our case, the feature term is input data. One second, I'll be back. Sorry about that again. Okay, so we're multiplying a bunch of inputs with a bunch of weights that are 0 and biases that are 0, and everything is just turning out to be 0. So let's see where they're going here. Let's see where they're actually taking us, because so far it doesn't seem like they're doing anything. Although a zero convolution can cause the gradient of the feature term I to become 0, the weights and biases gradients are not influenced. As long as the feature I is non-zero, the weight W will be optimized into a non-zero matrix, the first gradient descent optimization. Yeah, as soon as you take a step, then it will no longer be 0, and then things get interesting. The feature term is input data or condition vector sampled from datasets, which is naturally non-zero I. Yeah, I mean, what would be the point of feeding a non-zero input or a 0 input? Considering a classic gradient descent with an overall loss function L and a learning rate L. So this is the learning rate. And then this is the loss function. If the outside gradient, dl dz is not 0. Okay, so this is the gradient of the loss with respect to that specific 0 conv block. Right, so this 0 convolution block here is this here, right? And then they're taking the gradient of the loss with respect to that. We will have W star. So W star is the weight after one gradient descent step. This little, so one way to think about this, this symbol here, the circle with the dot in it that I've been taught is basically it's an arrow coming out at you. Right, so think of it that way. And like in physics, for example, it's basically like the curl, like sometimes, but here it's Hadamard product. Hadamard product. Hadamard product is element-wise product. Okay, binary operation that takes two matrices of the same dimension and produces a matrix of, so it's element-wise product. So this is exactly what it is right here. So A11, A12, this is some matrix, B11, B12, and you see how the resulting matrix is going to be the exact same size, right? It's going to be 3 by 4, 3 by 4. And each element is basically just going to be the individual multiplication of the elements. So here what they're saying is that the update, so the weights after your first gradient step are going to be the weights before your first gradient step minus the learning rate times the derivative of the loss with respect, this is a partial derivative, but the derivative of the loss with respect to the 0 conv with the Hamard product of the derivative of the 0 conv with respect to the weight. So this is actually just the chain rule here, basically, is what they're doing. The derivative of the loss with respect to the weights, you can basically chain rule that, right? And say that derivative of the loss with respect to the weights is the same thing as dl dz dz dw. So dl dw is the same thing as dl dz dz dw. But dl dw, you don't know what that is, but you do know what dl dz and dz dw is. So the whole point of the chain rule is that you're taking a partial derivative that you don't know how to calculate and turning it into a bunch of partial derivatives that you do know how to calculate. And that's basically the magic of deep learning. Okay, but they're basically saying that, yeah, this number is not going to be 0, so whenever you basically take your learning rate, and your learning rate is basically some small number, right, 0.001 or something like that, you multiply it by this, and you're going to change your weights by just a little bit. You're going to nudge them in this direction, right? At the end of the day, what you're doing is you're finding the direction in which your weights would better, you have some loss, and that if you changed the weights in a specific direction, the loss would go down, right? So that's, at the end of the day, all you're doing is you're finding the gradient, right? The direction in the loss space that you want to move your little weights. So that's what you're doing here. You're changing your weights. Okay. After this step, we will have dz di. So this is the derivative of z, the partial derivative of the 0 conv with respect to the input. So the partial derivative of this with respect to the input c. But the input c, they renamed it into I. So it's no longer vector c, it's now input map I. That is the sum of I, j over all c. So I think c here is channels. Yeah, and I is specific to the, I is basically the index of the height and width, I think, I and j. I'm not sure what I and j are. I think the I and j is just the indices of the weight matrix. Okay. Here we have a little bit more detailed of a architecture diagram here. ControlNet and Stable Diffusion. The gray blocks are the structure of Diffusion 1.5 since they use the same unit architecture. So they're using the more up-to-date version of Stable Diffusion, not 1.4, which is the original one. Right, so let's see. There's a lot of stuff here. So normal Stable Diffusion, the way it works is you have your input, which is basically noise, right? And then you remove the noise and create your image. And Stable Diffusion being a diffusion model, usually it runs multiple times, or it runs a bunch of times in a row, right? So that's what the time here means, right? A diffusion model operates multiple times, right? There's multiple inference steps. So you're going to have a 0 step, a step where t equals 0.1, 0.2, 0.3, all the way to 1. Usually the time is normalized. But the time encoder here is in charge of making sure that the time is presented and given to the neural net in a useful representation. The prompt here is basically your text. So in the case of the example up here, the prompt is a high quality, detailed, and professional image. And they feed that through some text encoder, probably clip, right? And you're not changing the weights of the clip model. You're not changing the weights of the time encoder. These are basically just are fixed. And you're taking every kind of brick inside your diffusion model, right? So these are all different bricks. I call them bricks. Block, I guess, is the terminology that they use in this paper. But you see here, this is kind of a U-net. So you see how it starts off big, and then it kind of gets to this little choke point in the middle here, and then it goes back to being big. So this is kind of a standard kind of UNet, where UNet is a pretty broad term, and it just refers to this kind of idea of having something that's very wide, and then it gets into a very narrow, kind of like a bottleneck, and then it goes very wide again. So the first part is the encoder, and then you have the decoder is when it goes back out. So every part of this, every block within this architecture is conditioned on both the time and the text. So this encoder block 1 here is being conditioned on the prompt. It's also being conditioned on the time. Okay, so that's basically this part here, which is the Stable Diffusion model. This is kind of just the generic diffusion model. And then here you have the ControlNet, right? So this is the extra stuff that they added for this paper. And every block here, they're going to add this zero convolution to it, right? So it actually seems like they only add the zero convolution to the decoder part of this UNet. They have here residual connections, so you see how this part here has a residual connection. The first part here has the prompt and time. So the same way that here in the actual Stable Diffusion model, every part of this UNet is conditioned with the text and the time. So you can see how here every single block has access to that. But here on the ControlNet side, only the first part, right? Only the encoder part of this UNet has access to the prompt and the time. So that's kind of interesting there. The time 3 here, that basically just means that there's 3 of these. So the same way that you would have many different attention blocks in a transformer, you're going to have a bunch of these decoder blocks, and they're basically just the same thing, just in one on top of the other. That's how you get bigger models, right? And then here you have a residual connection. So it seems like this one here, this SD encoder block 1, actually feeds something into this zero conv here. And this zero conv here takes the output of this. See, it's coming down through here. Then it goes into the zero conv, then it goes straight to here. So what's interesting here is that, to me, this has a very similar energy to residual connections, right? It's kind of the same idea of residual connections, where it's like, hey, let's take intermediate outputs from an earlier part of our neural net architecture and feed them directly into a later part of our neural net architecture, right? So same kind of energy. Obviously a kind of a different thing, but same kind of idea, I want to say. The condition is fed up here. So we still don't know how they're modifying these conditions, right? So like, so far they haven't really explained what they do to the condition. Non-zero gradients are obtained. In this way, the zero convolutions become a unique type of connection layer that progressively grow from zeros to optimize parameters in a learned way. Okay. ControlNet in image diffusion models. We use Stable Diffusion as an example to introduce the method to use ControlNet to control a large diffusion model with task-specific conditions. Stable Diffusion is a large text-to-image encoder or text-to-image diffusion model trained on billions of images. The model is essentially a UNet with an encoder, a middle block, and a skip-connected encoder. So this is the encoder, right? The UNet. This is a decoder. And then skip-connected decoder, what do they mean by that? What they mean is that the encoder blocks are here. You see this line? It's connected to a decoder block. So I call these residual connections. They're also sometimes called skip connections, but both of those mean the same thing. It's basically you have information coming from this block and going into this block. And you can see how all these blocks are connected here. There's residual connections here, or skip connections for all of these. So it's just skip connected decoder that is skip connected to the encoder. Both the encoder and the decoder have 12 blocks each, okay, and the full model has 25 blocks. 8 blocks are downsampling or upsampling convolutional layers. 17 blocks are main blocks that each contain 4 ResNet layers and 2 vision transformers. Okay, so they do have vision transformers in here. Each VIT contains several cross-attention or self-attention mechanisms. The texts are encoded by OpenAI clip. Okay, so we know that this part here, the text encoder, is a clip model. And diffusion time steps are encoded by a positional encoding. So the diffusion time step, right, normally it's normalized from 0 to 1, but here they're going to be using a position encoding. So every part of this Stable Diffusion UNet, right, knows how far along the denoising process they are, right? So when you are very early in the denoising process, right, you're performing the first inference step, you're probably going to be removing noise more aggressively. When you're very close to the end of the denoising process, right, maybe the 10th inference step, right, in however many steps you take in that diffusion process, you're probably going to want to remove less noise, right? So you're going to be less aggressive about your noise and noise removal. And that's why this diffusion model here, that's why you need to give it this time, right? Because it needs to know how much noise to remove. It's useful if it knows how much or how far along the diffusion process it is, so that it can remove either less or more noise. Stable Diffusion uses a pre-processing method similar to VQ-GAN to convert the entire dataset of 5x12 into smaller 64x64 latent images. Yeah, so this is just to make things faster, right? You reduce the dimensionality of your images. This requires ControlNets to convert image-based conditions to 64x64 feature space to match the convolution size. Okay, here we go. We're finally starting to understand what they're doing here. They're converting the image-based conditions to feature space. What does that mean? That means that the diffusion is happening in the latent space, right? So they're taking this image of the little bird, and then they're not taking the image. They're taking the image of nothing. It's just noise, and then they're eventually turning it into an image of a bird. But the noise adding and removing is happening in that latent space, right? So it's happening not in the image space, but in a latent space, like a little tiny, think of it like a little thumb, like a little tiny thumbnail that just, it probably looks like noise to humans. And because this zero convolution right here, right, the dimensionality needs to be the same as the intermediate input and outputs of this neural network block, right? The dimensionality here needs to be the same. So they need to make this C have the same exact dimensionality as this X. So if their C, right, is an input map, let's go back up here. If the C is an input map with HWC, right, where this is 64x64, then they need to convert the condition, right, this Canny edge image, into also the same dimensionality, which is 64x64, right? So they need to convert the image-based conditions, which basically is just that edge image, into a 64x64 feature map or latent image, such that they can basically do the addition that they're doing to match the convolution size. We use a tiny network E. So, okay, so they're introducing a new network here of 4 convolution layers with 4x4 kernels and 2x2 strides activated by ReLUs. It's like a little tiny mini convolutional net to encode image space conditions into feature maps. Okay, so it's starting to get a little bit more complicated, where it seemed like this was pretty standard, right? Okay, we have our Stable Diffusion. It's a UNet. There's skip connections between the encoders and the decoders of this UNet. You're conditioning every block in this diffusion model with both the prompt that has been fed through a clip text encoder and then the time, which is just fed through standard kind of position encoder. And then we're going to build this parallel network next to it, which we're going to call the ControlNet. And the ControlNet is basically just going to be initialized to 0. So initially it does nothing, right? You can basically feed everything through it, and because it's all 0, you're just going to basically get the same thing out. But then we're going to start pushing gradients into it, and over time these will become non-zero, and then they'll actually have an impact on the diffusion model. They'll actually start to change the inputs and outputs of this diffusion model. And this ControlNet that we're kind of like parasitically attaching onto the Stable Diffusion model, we're going to feed it with a condition. And this condition is going to be an image, right? This Canny edge image. And we need that condition to be the same kind of dimensionality as the input to our diffusion model. And unfortunately for us, the input to this diffusion model is a latent image. So we need to figure out a way to turn our Canny edge image into a latent image. So how the fuck are we going to do that? So the way that we're going to do that is we're going to make a new network. We're going to make a different network, a tiny little convnet called E, or big epsilon. And we're going to feed our Canny edge image into that, and it's going to give us a latent image CF. There's a lot of stuff here, right? You have your clip network, you have your diffusion model, you have your tiny network, you have your ControlNet. So there's a lot of different pieces to this, right? And actually, the way I'm thinking about this, I'm like, they should have totally used a vision transformer for this. They just used a little tiny convnet, but I wonder if they would have used a vision transformer, whether you would get better results. So for you guys listening to this, you should totally see what happens if you put a transformer there. This network converts 5x12, 512 by 512 image conditions into 64 by 64 feature maps. We use ControlNet to control each level of the UNet. Note that the way we connect the ControlNet is computationally efficient. Since the original weights are locked, no gradient computation on the original encoder is needed for training. This can speed up training and save GPU memory, as half of the gradient computation on the original model can be avoided. Training a stable diffusion model with ControlNet requires only about 23% more GPU memory and 34% more time in each session. They tested this on a NVIDIA A100 with 40 gigs of memory, which is pretty huge. That's not something that you would have available, that you would have as an individual person with a GPU at home. To be specific, we use the ControlNet to create the trainable copy of 12 encoding blocks and 1 middle block. The 12 blocks are in 4 resolutions: 4, 32, 16, 8, with each having 3 blocks. The outputs are added to the 12 skip connections and 1 middle block of the UNet. Since standard diffusion is a typical UNet architecture, this ControlNet architecture is likely to be usable in other diffusion models. Yeah, you could apply this technique to anything, right? Obviously, you're not going to, the ControlNet, the design of the ControlNet is going to be very specific to the design of the diffusion model. So if you had a different diffusion model, you would have to make a completely different ControlNet for it. So the ControlNet parasite, I like this word this term that I made up for it, but the ControlNet parasite is specifically designed for this diffusion model architecture, right? The number of these blocks, the size of these blocks, the size of the input, the size of the output, all of those need to match exactly with the diffusion model that you use. Training. Image diffusion models learn to progressively denoise images to generate samples. The denoising can happen in space. Coded from training data, Stable Diffusion uses latent images in the training domain. In context, the terminology image, pixel, and all refer to the corresponding concepts in the perceptual latent space. So when they refer to the image, they're really referring to the latent image. When they refer to pixels, they're really referring to individual values inside that latent image. And when they refer to denoising and noising, they're referring to denoising and noising in the latent space. So, little caveat here. I like that they said this because sometimes in diffusion papers it can get complicated and you start thinking that they're actually doing things in image space, but really it's all done in latent space. So it's good that they do that. Okay, so they start with an image Z0. This is not an image, right? It's a latent. Diffusion algorithms progressively add noise to the image and produce a noisy image. Noisy image. And then T being how many times the noise is added, right? So T is your time, and it ends up being how many inference steps you're going to perform as part of your diffusion process. Given a set of conditions including time step T, the text prompt CT, as well as task-specific CF, image diffusion algorithms learn a network to predict the noise. Right? So if you can predict the noise, you can remove the noise. And that's how diffusion models work. They remove the noise because they can say, given this image, here's what I think the noise was that was added to it. And then you simply subtract that from the image, and then slowly over time, an image appears out of the noise. Okay, so this here is expected value. So here we have the loss, which is the overall learning objective of the entire diffusion model, which is basically this is the loss that produces the gradients that you push through your diffusion model. The loss is the expected value for a given image or latent image at a specific time, right, at a specific inference step with a specific text prompt converted into a latent vector with a specific noise condition converted into a latent image, or at least it matches the space of this Z0. So here, CT and CF are actually, this is not great names for these variables either, because CT is probably going to be a very different dimension than CF. CF is actually going to be the same dimensionality as Z0. And then this little epsilon here, which is sampled from a Gaussian. So this basically just means Gaussian noise, right? The N is the normal distribution or Gaussian. 0 means it's centered on 0, and then 1 means the variance is 1. And then here, it's the expected value for all those different things, right? So the loss is optimizing all of these. And here you have the L2 norm, or L2 difference, right? So it's basically just like the difference between these squared and square rooted. And then here you have the noise that is being predicted. So you have your network epsilon theta, right? So some network that is parameterized by parameters theta, and it predicts the noise. And then it predicts the noise using the current image, the time, current text, and the current conditioning. And then you want the noise that it predicts to basically be the noise that is added. And then over time, this little network E theta is going to get better and better at predicting that noise for specific contexts. During the training, we randomly replace 50% text prompts CT with empty strings. So, okay, so they're doing the guidance sampling thing here. This facilitates ControlNet's capability to recognize semantic contents from input conditions, Canny edge maps, or human scribbles. This is mainly because when the prompt is not visible for the SD model, the encoder tends to learn more semantics from input control maps as a replacement for the prompt. Okay. I mean, I think it's just kind of a form of regularization. We discussed several strategies to improve the training of control nets, especially in extreme cases when the device is very limited or very powerful. Okay, this is interesting. They're going to start talking about how you're going to do this differently on a large cluster versus a laptop. Small scale training. When the computation device is limited, we find that partially breaking the connection between the control net and the Stable Diffusion can accelerate convergence. What does that even mean? By default, we connect the control net to the SD middle block and the SD decoder block 1234, as shown in figure 3. We find that disconnecting the link to decoder 1234 and only connecting the middle block can improve the training speed by a factor of 1.6. Damn, there's laptops with RTX 3070s? That's pretty crazy. When the model shows reasonable association between results and conditions, those disconnected links can be connected again in a continued training to facilitate accurate control. Okay, so these connections here, the 0 comms going into the decoder, you can get rid of these and not have them. And that'll reduce the overall memory, the total amount of computations that you need to do, and then it improves training. So that's kind of what they were saying here. Partially breaking the connection. Large-scale training. Large-scale training refers to a situation where both powerful computation clusters, so this is a server rack of NVIDIA A100s with 80 gigabytes, so this is huge. And a large data set, at least 1 million of training pairs are available. This usually applies to tasks where data is easily available, the edge maps detected by Canny. In this case, since the risk of overfitting is relatively low, we can first train control nets for a large enough number of iterations, and then unlock all the weights of Stable Diffusion and jointly train the entire model as a whole. Okay, so there's kind of a two-part training going on here. There's the first part of the training, they lock the diffusion model, and then they're only pushing gradients into the control net. And then after 50,000 steps, they unlock the diffusion model and they push gradients into both of them. So you have kind of a two-part training there. It's very similar to the lit paper locked image tuning that we saw, where basically you have kind of more complicated locking and of different parts of these like multi-system models, multi-model systems, where you have multiple different models interacting and feeding inputs to each other, right? When you're training these, you don't want to push gradients into all of them at the same time, and you can contrive these kind of more clever training schemes where you have one locked, and you're pushing gradients into the other one, and then you lock the other one and push gradients into this one, and so on. So specifically here, what they're doing is they're pushing gradients only into the control nets, and then they're pushing gradients into both the Stable Diffusion model and the control net. We present several implementations of control nets with different image-based conditions to control large diffusion models. Okay, so they have Canny edge detector. Canny edge detector to obtain 3 million edge-to-image caption pairs. Model is trained with 600 GPU hours on an NVIDIA A180 gig. Base model is Stable Diffusion 1.5. So how do they get this data set here? So they take a bunch of image caption pairs, and then they feed the image into some kind of generic Canny edge detector. It says here random thresholds. What they mean by that is that the Canny edge detection algorithm has magic numbers in it, right? There's like specific numbers in there where you have to decide what is the threshold, right? Like how much does the color need to change? How big does the gradient need to be in this pixel space for you to consider that an edge, right? And the threshold will change kind of the aggressiveness of the Canny edge detector. So rather than like choosing some threshold which is magical, they're basically just randomly picking thresholds and then using that to generate a very large data set, 3 million here, of image caption pairs with a corresponding edge image as well. And then they train that for a long time on a big ass GPU. Canny edge alter, so this is a different. Okay, wait up, no. We ranked the image resolutions of the above Canny edge dataset and sampled several subsets. Okay, so they're messing with the image resolutions. Okay, so basically they're doing the same. It's basically the same data set as this Canny edge here, except they're basically splitting it into smaller data sets that have either small resolutions or big resolutions. Huffline, learning-based deep Huff transform to detect straight lines. Okay, so this is also going to produce kind of a image that has edges. And then use blip to generate captions. So blip, this is the model that we saw on Monday. This is a captioning model that you give it an image and then it'll produce a little sentence that describes that image. We obtain 600 edge to image caption pairs, and we use the above Canny model as a starting checkpoint. Okay, so this is interesting. They make a different data set here, right? So now they have a data set that is starts from an image caption data set, but then for every image in that data set, they calculate the edges, right? And they do that using this Huff transform. And they don't actually train this one from scratch. They train it from the Canny edge model. So they take this model here and then they push more gradients on it for another 150 GPU hours. Okay. Damn, they have a bunch of these. Holy shit. HED boundary detection. That ED boundary detection. Okay, so it's basically another kind of edge detector. Holistically nested edge detectors. They're all just different types of user sketching. So this is a little bit more interesting. We synthesize human scribbles from images using a combination of HED boundary detection and a set of strong data augmentations. Okay, so they take this HED boundary detector and then they kind of mess up the images a bunch. So they randomly mask out a random percentage of the scribble, random morphological transformations, random non-maximum suppression. So they're kind of messing with it and then saying, okay, that's kind of the equivalent of a scribble. We use the above Canny model as a starting checkpoint and then train it again for another 150 hours. So a bunch of these use the Canny model as the starting point. That's interesting that not all of them, you would think that all of these would just start from scratch. They would train all of these from scratch, but it's interesting that these are all, or the Huffline and the user sketching are all trained from a starting point of the Canny edge. We use learning-based pose estimation method to find humans from internet using a simple rule. An image with a human must have at least 30% of the key points of the whole body detected. Okay, we obtain 80K pose image caption pairs. So you have a data set with image and captions, and they're using a pose detection model to find the pose. So detection. You guys haven't seen this type of stuff before. Here we go. Pose estimation. Example, but the pose is basically a set of key points. So every point here is known as a key point. And then each of these points, right, there's some specific structure to them. So you have like a key point for the elbow, a key point for the shoulder, a key point for the hand. And then what a pose detection model does is it takes an input, it takes like an image, and it'll tell you this key point corresponds to the hip, this key point corresponds to the hip, this key point corresponds to the shoulder, so on. And then you connect all those dots and you basically get a rough human pose. But because pose detection models, they're basically, every single frame is fed into the pose detection model. So you can see how it's like jittery, right? Problems with. But another thing is that they want at least 30% of the key points of the whole body detected. So here, right, all of the key points are detected. Here in this one, none of the legs are detected. So basically they make sure to filter it so that only full human skeletons are there. And then blah, 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 train with human skeletons. And then they train for another 400 hours. Human pose. Learning pose estimation model. Find humans from internet using the same rule. We obtain 200K, another 200K pose image caption pairs. Can we highlight this? Blah, blah, blah. Train for another 300 hours. There's a lot of training. There's a lot of data sets and training. I wonder who paid for all this. Okay, semantic segmentation. So segmentation. Segmentation is the task of taking a 2D image and then basically determining what the class label for every part of the image is. So for every pixel in this image, you're defining a specific class. So here in a autonomous driving dataset, for example, you would split up every pixel and you would say, is this pixel a road? Is this pixel a car? Is this pixel a building? And then so on, right? Sometimes it's not pixel level where you're classifying every single pixel. Sometimes it's polygon mask kind of thing, right? Where it's like predicting a kind of polygon that surrounds the object. So there's a bunch of different types of segmentation, but largely it's the output, which is a segmentation image, is basically a version of the image with class and category specific labels to it. So Coco is a data set that has segmentation annotations to it. So basically that other data set. They train that for another 400 GPU hours. It's interesting how they're using different stuff here, right? So here they have an NVIDIA 3090. Here they have an NVIDIA A100. So some of the experiments, they ran it on a cluster. This is a server GPU, right? And some of these, they ran it on a local computer. So it's interesting that they didn't run all these experiments on the same hardware. They ran it on different hardware. The 8020K captioned by blip. So this is another 164 segmentation image pair, so different from Coco. This is 8020K. They use Midas to obtain 3 million depth image caption pairs. So Midas is a model it's a monocular depth estimation model. So basically you give it an image and then it'll give you a depth image. So Midas depth image. So this is a depth image. A depth image basically is an image that tells you how far or how close every single pixel is to the camera. So you see here in this image of the cowboy, obviously the cowboy is closer to the camera than this wall. So that's why the pixel values here are different from the pixel values in the back. And there's models that will basically take an image and then produce a depth image. And I generally don't like these kind of monocular depth estimations because they're not going to get, they have a lot of noise and they're sensitive to errors. So I think it would have been nicer if they used a real depth data set. Like there are data sets of actual depth images where it's like coming from a structured light sensor or a LiDAR or some kind of like explicit depth sensor. But I don't think it might be the case that they don't get as many as they want. Right here you have 3 million depth image pairs. So maybe data set with true depth wouldn't be big enough and would probably be too narrow in terms of the domain for them. We rank the image resolutions of the above depth dataset to sample a subset of 200K pairs. This set is used in experimenting the minimal required dataset to train. The diode dataset, captioned by blip, we obtain 225,000 normal image caption pairs. So normal maps is it's similar to a depth image. So normal map image. In a normal map, this is, but you can think of it like, yeah, this is a good. So a normal is when you have a surface, then the normal is a vector that basically. So a normal map tells you what the basically the direction of that surface is. So for something like a sphere, right, you're going to have the normals are going to be very continuous, right, because sphere. For something that looks more like a square, the normals are going to be all the same for each face, and that's how you get this kind of like more blocky looking thing. So the normals are basically telling you what is the orientation of all the surfaces in this image. In the same way that there's models that will give you the depth for a given image, there's also models that will give you the normal map for a given image. But here, I think they have an actual, they use an actual data set that has explicit normal maps. We use the -30 to compute the depth map and then perform normal from distance to achieve coarse normal maps. We use the above normal model as a starting point. Okay, so actually they do both. They have an explicit normal map data set, and then they have a normal map data set where they are approximating the normals. Then finally, the last one here, cartoon line drawing. We use a cartoon line drawing, extract line. From cartoon illustrations. By sorting the cartoon images with popularity, we obtain the top 1 million line art cartoon caption pairs. Kind of interesting. You can get over 1 million cartoon images. Cool. Wonder where that data set is. It's iFood. All right, there you go. The word waifu is officially inside the machine learning literature. Experiment section. All right, we're finally getting to the experimental settings. All results in this paper are achieved with CFG scale at 9.0. The sampler is DDIM. We use 20 steps by default. So this is how many time steps there are, right? So in a diffusion model, you're performing a bunch of inference steps. Here, they're basically doing 20 of them. We used 3 types of prompts to test the models. Not a prompt, default prompt, automatic prompt, or user prompt. So what is a default prompt? Since Stable Diffusion is essentially trained with prompts, the empty string might be an unexpected input for the model, and SD tends to generate random texture maps. A better setting is meaningless prompts like an image, a nice image, a professional image. In our setting, we use a professional, detailed, high-quality image prompt. Automatic prompt. In order to test the state-of-the-art maximized quality of a fully automatic pipeline, we also try to use automatic image captioning methods. So this is a flip model to generate prompts using the result obtained by default prompt mode. Okay, so basically it seems like they can do 2 different things here. They can basically use just kind of a generic prompt, and then once they have this generic prompt, then they use blip to caption the model, and then they feed it again with the prompt that blip gave them. So there's kind of a multi-stage pipeline here as well in terms of like what prompt you're using. Okay, so they present their results in a bunch of figures below. We're probably going to scroll and find a bunch of pictures. Figure 20 shows a comparison of a model trained without using a ControlNet. That model is trained with the exactly same method. Adding a channel to the Stable Diffusion and training. Figure 21 shows a training process. We would like to point out that sudden convergence phenomenon where the model can suddenly be able to follow the input conditions. Canny edge-based control. Yeah, they kind of end it quickly here, so it's kind of interesting. And like they were very, very verbose about everything that they were doing, and then suddenly they just say, okay, and we're done, and you can just go ahead and look at all the pictures. So let's go ahead and do that. So here the input context is a Canny edge image. So we have this image here. I think the original image is of a woman in the Great Depression. So default is with no prompt, I think, right? No, default is just a professional, detailed, high-quality image. Automatic prompt, so this is where they feed the default prompt. They get this image, then they take this model and they feed it through blip, which will give them a caption. So the blip model goes from this image into a man with a beard sitting with 2 children, and then they feed, and then basically they do the whole thing again, and now they're feeding this input with this prompt, and you get this. So seems like it maybe makes it a little bit better, but I don't know. Then user prompt. So this is now the authors are coming up with this prompt here, and then they're basically feeding this, and then this prompt, and then Stable Diffusion is doing the rest. The one thing to notice here is the hands, right? So notice how this hand is actually pretty good for Stable Diffusion standards. Man in a white suit and tie, showing how they can color. Note interesting kind of the interesting directions here that Stable Diffusion goes. Like for most of these, it decides to do this kind of like outside button, inside button type of situation. But for this one, it actually opens up the vest, have kind of like an inside vest. Cute cat in the garden. These are really. Man standing on a cliff. Man on a hill watching a meteor. So you can see how initially this part of the Canny is interpreted as a river, or it's interpreted as the sun. But then when they add the watching a meteor, it's interpreted as a meteor. That's very interesting. Robot heads with gear, and then adding cybernetic cyberpunk, and it kind of adds kind of these cool colors. Made of wood, change wood texture. There's still some mistakes here. You see kind of the around the edges here. It's a little weird and wonky. Modern house with windows, Minecraft house. That's pretty cool. Look at this. This applies Minecraft. Stable Diffusion is trained on Minecraft. I guess that makes sense since Minecraft would be a good source of data. Ooh, this one's kind of interesting. So you can see here with a building on a city street, it very clearly follows the fact that this is a building. But then once you say, if you say inside a gorgeous 19th century church, Stable Diffusion figures out some way to make this the inside of a church, even though it's very clearly the outside of a house. Desk in a room, hacker's room. Turtles. These are all user scribble, kind of like an edge detect, or kind of like a. So these are different inputs, right? So here you had the Canny edge. Here you have the Huff line, and the user scribble, like the way that they train this one is they basically use the Huff line, and then they kind of just very hardcore data augmented it. Robot Ox on the moon, UE5 rendering, ray tracing, kind of get that weird effect. Egyptian elephant sculpture. Cool, look like the Sphinx. This is now HED edge. This is a different type of edge detection. Very good at the individual details. Boy elephant sitting on a table. These are really high quality human. Like, look at the hands. Look at these hands. They're still a little weird. Like, you know, like, look at this. Like, we don't exactly know what this finger represents or what it means. But that is very clean. Like, pose model. This is revolution. Look at this. Look at how here, adding the word music, it adds the guitar. Michael Jackson concert. They're pretty good. I mean, the face is still a little weird. Like, this face is weird. But, like, these costumes are on point. And he even has the kind of, like, vintage camera effect. I'm not actually, like, I don't know these costumes well, but I'd wonder if, like, someone who's an expert on kind of, like, Michael Jackson, like, are these actual costumes, like, one-to-one, or is this, like, a mishmash of all the different costumes that he's worn? Images are not cherry-picked. This is segmentation maps. Pretty good. So you see here, Coco segmentation maps are actually polygons versus these type of segmentation maps are pixel. So every single pixel here has a corresponding label versus here, you see how originally they're kind of polygons. So you have this kind of like probably not a good edge. So the problem with the segmentation is that the edges aren't very clean, right? So like it's very blobby. And it's actually kind of surprising that, like, for example, here with the fan, the fan actually ends up looking quite nice, even though the input here is quite blobby, and the same thing here, right? So like the ears, the fact that it like kind of is like square looking here, it doesn't actually seem to affect it a lot, which is great. Here's a normal maps. So this is kind of the orientation of every single surface in the image. This is EMAD. This is the Stability AI president, CEO, founder, I don't know. Images in Midas depth. This is a depth image. Him as a stormtrooper. Okay, so here's an interesting one. Here's the difference between training on large-scale NVIDIA A100 hours for more than 2,000 GPU hours versus training on a single NVIDIA RTX 3090 for less than 1 week. So, I mean, this goes to show you that you don't need the huge ones to fine-tune a model, but I don't know. I think long term, the world where you can train things at home is going away and everything's just going to be cloud training. Not because you won't be able to do it at home, but I think that the cost of cloud computing is just going to get so cheap, and there's going to be so many different competing cloud services that are basically just throwing free credits at you, trying to get you to use their service, that it's easier for someone to just use the free credits on like a cloud computing service to do what they want rather than kind of buying a GPU, maintaining it in-house. This is probably the waifu Stable Diffusion, but I don't know. I'm not a very good judge of quality when it comes to waifu. I know that the people who are into the anime models are like very particular, and they have a very keen eye in terms of like the exact little details that they're looking for. But I mean, these seem pretty good to me, right? It looks like it's all coloring within the lines. Like if you look here, the kind of like the different colors of the dress, like this seems really impressive to me. Here's diffusing with masking. So this is kind of a combination of like in painting with the Canny edge model. This is a different work. Piti, P-I-T-I. I mean, this blows them out of the water. I feel bad for whoever wrote P-I-T-I. So I think here they're comparing to add the channels to an input layer. So I guess that there's like some kind of official recommendation from Stability AI where you can add the depth channel, something like into the original image, and then you can get a similar effect, but it seems like the ControlNet is actually cleaner. It's also crispier, right? Like look at the crispiness of this image compared to that. Like the individual lines are just more well-defined still. Okay, this is an interesting image. This is basically over time. So it shows you, if you start with this is the condition. So this is the Canny edge image, which is turned into a latent image, and then the latent image gets fed into the ControlNet, and then the ControlNet kind of influences the inputs and outputs of the diffusion model. So here you can see different training times. So I think they do say that they train the ControlNet first, and then they allow the gradients to go into the Stable Diffusion as well. So I wonder at what point whether they tell you that. It doesn't seem like they tell you that, but they said it was 50,000 steps, so somewhere between here and here. So at 100 steps, it doesn't matter, right? So the prompt is Apple, right? So at 100 steps, the ControlNet doesn't have any influence on the diffusion model. So when the diffusion model is given the word Apple, what it's doing is it just gives you an Apple computer, right? This is just kind of a standard text-to-image model. But then as you go further and further into training, right, the ControlNet is the signal coming out of that is bigger and bigger in magnitude, which means that it kind of has more and more control over the actual output of the diffusion model, right? Where the output of the diffusion model is just the noise that gets removed. So you see here how here it's still just kind of in text to image mode, where it's just kind of going from Apple, and the Apple is very strongly correlated with Apple computers. So it's like all just Apple computers and kind of like random text to image stuff. And then there's kind of this point where it suddenly is like, they call it sudden convergence, where now suddenly the ControlNet has achieved control, right? It's now the magnitude of the signal that it's feeding into the stable diffusion model is strong enough that the outputs that it produces are always matching this edge detection model, or this edge input, this condition. Because we use zero convolutions, the neural network always predicts high quality images. At a certain point of the training step, the model suddenly learns to adapt the input conditions. I would say at a certain point in the training step, the zero convolutions have sufficiently grown in magnitude that they begin to irreversibly impact the diffusion model's outputs. So here they show with different dataset sizes. So they fine-tuned the Stable Diffusion model for specific types of control inputs. So for the input Canny edge, right, they created 3 million. But here they show you how if they fine-tune it with a smaller data set, you get different results. And you can see here how fine-tuning with 1K, pretty shit. But then fine-tuning with 3 million, this is pristine. Look at the texture of this main. Okay, so this is room plus, that's the prompt. This is the source image. The source image is used to create a canny edge, a depth, a normal, an HED, a line, and a scribble. And then you can see the different results from the ControlNet. So these two images here, are basically the prompt, and then this canny edge image. These two images here are the prompt and then the depth. So you can compare which one is better. I feel like the edge is the best here. Canny edge is just very good. Depth maybe gets a little bit. HED, normal, line, scribbles. These are all pretty good though. But I think Canny Edge is the best. And also part of the reason it's the best is I think it has the most training. Here you have the same kind of thing. Which one of these modalities for the context is the best here? Canny Edge, depth, normal, HED, scribbles, or lines. I still feel like Canny Edge is the best. Yeah, so here you see depth Midas. So what this means is that this isn't true depth. So you can get real depth from an actual sensor, like a structured light sensor or a LiDAR camera, and then you would have an actual depth for an image, but these are depths that are output from a different model. So Midas is a model it'll take an image such as this and it'll produce this. And the problem with that is that this is not ground truth, right? This is not the actual real normal map. This is like an approximation of the normal map. So you're introducing noise here by using this Midas model to give you the depth and give you the normal map. Versus I feel like something like a Canny Edge, it does not introduce noise or as much noise, right? Because it's not like a learned algorithm. It's just a generic, like all the information that the Canny Edge is showing you is basically just a property of the actual source image. Clean. That is very clean. And even with very primitive scribbles, you can actually control quite well. This is awesome, guys. So we did it. We finished the entire ControlNet paper, all 32 pages, front to back. been a journey. This is really impressive stuff. Very cool. I understand the hype. I see where people are coming from. I think this is going to be huge for kind of 2D control. I think this is, this man here is definitely hyped about this. You're probably going to start seeing this in Stable Diffusion's product as quickly as possible. I think you're going to start seeing this in a bunch of different AI generative art tools as quickly as possible. There's going to be some pretty crazy stuff that people start doing with this, but it's a relatively simple concept, right? It's basically you have your diffusion model, right? Your UNet diffusion model, which is taking as input a prompt fed through a text encoder and a time, right? 20 different steps in this paper. And then you're basically making this kind of like parasite shadow model that has a very, very similar kind of architecture to the original diffusion model, and then just basically has all these kind of like connections to each individual layer. And this ControlNet is initially, it's initialized as 0, right? So this is not randomly initialized. This is all the weights here start as 0s. And then you're taking a image, such as a Canny edge image. You're first turning it into a latent, the same way that you would turn your image into a latent. And then you're using that latent, I think what they call here a condition, to basically condition via the ControlNet all the different parts of the diffusion model here. And you can use anything here, right? As long as the dimensionality of this matches the dimensionality here, right? As long as all these dimensions match and the tensors are the same size so that you can add them together, you can put anything in here. And they do a bunch of different types of things. They add segmentation, poses, sketches, different types of edge detectors. So sky's the limit, and I imagine that people will actually probably combine these. They'll probably have multiple conditions, maybe multiple control nets. But yeah, that's the basic kind of idea. Very, very cool. Hope you guys enjoyed that. Hope you guys understand control nets a little bit better. If not, if you have any questions, definitely pop on the Discord to ask those questions. Thank you for listening. Like and subscribe, and guys